Okay, so 5b, part 2, finding the distance between 2 points with the same, that should say same, latitude. So you remember about latitude is that when you have the Earth, latitude is all based on the equator, and then you go up from there, right? There are 3 lines of latitude above and below. Now, but except for the equator, all lines of latitude are not great circles, they're small circles, right? And so we're going to have to use a slightly different process to find the distance between 2 points. Now we're still going to use that fact that the angular distance can be used, but if you'll think about a line going through the center of the Earth, what's happening as you go up? The radius of these is getting what? Smaller and smaller as you go up, yeah? So we have to use another process to be able to find that radius. And then we can plug the radius into the formula. Well, the good news is this, that because these lines are parallel, they have properties that make your life easier even if you don't know them and you don't care. Because the angles of lines with transversals of parallel lines have properties that are standard, we can use a formula very similar to the one that we've already been using. Okay? So here we go. With the exception of the equator, now, why is the equator the only line of latitude that's an exception? Because it's a great circle, right? It goes all the way around the planet with the center as its circle. So the equator behaves just exactly like any line of any meridian. Okay? Shh, guys. With the exception of the equator, to find distance between 2 points, you're going to take something very familiar, 1.2 kilometers, times the cosine of theta. Cosine is a trig function. Who cares? If you'd like for me to explain it to you, I'm happy to at the end. No problem. Theta, we use theta just to stand for any unknown angle. Remember that? We've talked about that in our notation before. Times the angular distance, which is something else that we've talked about a lot. The angular distance is that distance. You either added those 2 things or subtracted the 2 things to be able to find the distance between them.
Yeah, how do we work with the angular?
So this bit and this bit are the old formula that we used. The only thing that's new is this. You need know nothing about trigonometry in order to make this work, though. Your calculator is going to do all the math for you. Yeah. So get your calculators out because you're going to use them, because I'm not doing the math because I cannot do the cosine of anything in my head. All right. Now, where theta is the degree latitude. Now that's given for you in the problem. So if they're at 48 degrees latitude, that's just a given. So you just read that straight from the problem. The 2 cities or 2 points on the globe, whatever you're looking for, are going to be at the same degree. Okay? And the angular distance is in reference to the prime meridian. What do we know about the measurement at the prime meridian? How many degrees is it? 0 degrees, right? The prime meridian is where where longitude is zero. It's right. That's that That's that line, that imaginary line through Greenwich, England, that divides the Earth into the longitude units, right? Okay? So, let's talk about finding the angular distance when we're dealing with latitude. It's the same process. It's just that you're dealing with small circles, all right? And to give yourself an indication of that, when we do these, we're still going to first make a drawing. But to remind yourself that we're dealing with small circles and therefore a different formula, we typically draw an oval. Because remember, these small circles are a slice through the Earth, not the whole round. Does that make sense? Okay. Then, we're going to label the prime meridian at 0 degrees. Now, just like the equator, it doesn't matter where you put it, but we usually put the equator in the middle. So what we usually do is we just call this the prime meridian. That's the line of longitude that's at 0 degrees. And remember, it divides the Earth into east and what? West. Okay? So you remember some of those drawings? Next, label your 2 points. All right, so you're going to label your 2 points just like you did. And if both of those points are east, then you're going to have 2 points over here on the east. Right? Just like we did with the equator. If one is west and one is east, you'll have one on one side, one on the other side. Right? And the location of those points are going to tell you what you need to do to them to find the angular distance. So do you remember? If they're on the same side, so let's say they're both east, then what we're looking is for the distance between them is just that little part there. So in other words, we need to get rid of part of it. So we'll subtract them. Just like when they were both on the same side of the equator. It's exactly the same process. Okay? So if they're on different sides of the prime meridian, you're simply going to add them. So for example, if you wanted the distance between these 2 points, they cross the prime meridian. Therefore, you have some on the east, some on the west, and you need to account for all of it. So you're simply going to add them together. And whatever value you get is going to be the angular distance.
So then subtract difference and then add.
If they're on the same side, you subtract. If they're on different sides of the prime meridian, then you add. Exactly the same as on the equator. When we did those yesterday, if they're on the same side of the equator, you're looking for a smaller piece, you need to subtract some out. If they're on different things, you need to widen your angle, so you're going to add them. Okay? The only difference is here we're using the prime meridian instead of the equator. And technically, you could do the same drawing and just call the equator prime meridian. The only reason that we do this business is to trigger the idea that you're going to use a different formula because of the different location, because of latitude. Because they're small circles, we're going to have to put that cosine business in there. Right? So the only reason you even make the drawings different is because of that. Now, I've got one more scenario for you. Let's say we're flying from one city to the other, and I want to fly east. Well, if I'm going to fly east, that means I'm going to go that direction, yes? Which means that in order to get there, I have to go all the way around the planet to the other one. So let's say that this one is theta degrees. How would I find the distance all the way around? How many degrees is a whole circle? 360 minus theta. that doesn't just apply for great circles, that applies for any circle, right? Okay, so don't think that because the circle got smaller that you're not going to use 360 if you're doing the whole circle. Okay? All right, so pay attention. And the only time they'll ever ask you for that is if they're really specific about if you were going to fly east, or if you were going to fly west, right? Okay? From a particular location. So then, simply use the formula. 111.2 times the cosine of theta times the angular distance. Now, all you're going to do now is just plug this into your calculator and let the calculator do your work. And there is only one mistake you can make when you do that. So, because if you put in cosine, then your calculator is automatically going to open up a bracket. And if your calculator opens up a bracket, then what do you have to do? Well, yeah, but after you put in the angle, you have to close the bracket. Because once you put the angle in there, whatever, anyway, it'll be the angle from the problem. Then if you did the angular distance without closing the bracket, then it'll take the cosine of that whole product. And that's not what you want. So be careful and make sure you close that bracket after you enter the angle. Otherwise, it's going to really make some really bad mistakes. Pardon?
Is it the west cosine?
Yes. Yeah. And I'll be happy to explain why if you want to. All right, so let's just run through an example very quickly of one of these. Now, still doing this for the recording. I'll do the math. I'll walk you through it and tell you what to do, but you have to do the math for me because you've got the calculators, okay? All right? So let's just go to the book. I don't want the equator. Hold on. Same meridian. I don't want that. Okay, here we go. The position of Salzburg is 48 degrees north, 13 degrees east, and the position of Seattle is 48 degrees north, 122 degrees west. Find the distance around the 48th parallel of latitude between Seattle and Salzburg. So this time, they're not on the same, they don't have the same longitude, they have the same latitude. And even if they hadn't told you that they're on the same latitude, you could have used the fact that these first two numbers are the same to know that they're on the same latitude. So, you could have just used the fact that you know that the first number of degrees is always latitude, the second one's always longitude. So they have different longitude, which tells us that we're going to be using the second formula. So we know that Seattle is at 48 degrees, 122 west, and Salzburg is at 48 degrees, 13 degrees east. Unless I have something covered up. Yeah, 13. So if that's enough information to be able to find the distance between them. So we have our information. Let's just go to some notebook paper and work these, remembering you guys are going to do the math for me.
What is it? How do you know who's on the sky?
All right, here we go. So, since we're dealing with latitude, we're going to draw not a great circle, right? So, instead, what we're going to do is we're going to draw an oval, right? And that should tell you that you're using something different. The point down here at the bottom, we're going to call the prime meridian, which is at 0 degrees, right? And we know that goes all the way through the center of the earth. We have Seattle at 122 degrees west. Remember, west is this way, east is this way. So 122 degrees west is Seattle. Do I have to get it perfect? Do I care?
Yes.
Could I have put it there?
No.
Sure, you could have. It doesn't matter. As long as you get the numbers right, I don't really care that much about the drawing. So that means from Seattle to the center of the Earth, there's a line there, right? That's its radius. The other one, Salzburg, is 13 degrees east, so that's just over there a little bit. So drawing a line from there, that's its radius. Yes? Are they on the same side of the prime meridian, or do they cross the prime meridian? They cross it. So that means that I need this whole total distance. So therefore, I'm going to be taking those two angles of longitude and adding them together. So what is 122 plus 13 going to give me? Sorry, what? 135. Thank you. And so that's my angular distance. Okay? That's this big angle here, 135. It's all good? Now, all I have to do is plug into the formula. First part of the formula is still the same, 111.2. That never changes. Then I need the cosine of the latitude. What was the latitude for both of them? 48. You never have to find that. It's always a given. Right? So there's never any calculation to find that one. Brackets, please. Times, what is my angular distance between them? And that's all I need. So now what we'll do is just plug that into your calculator. So 11.2, and if you want to multiply these two first and times the cosine, or do the cosine first, it's all multiplication. So does the order matter? Not at all. So if you want to multiply them in order, you can. Otherwise, it don't matter.
Brackets, right, sir?
You have to have the brackets. It'll put the first bracket in for you. So put 1112 times the cosine of 48 in brackets, but you don't have to put the first bracket. Once you hit cosine, it should automatically open up a bracket. Put 48 in there, then close the bracket. And then times 135. Anybody want to give me an answer?
10,044.9.
Okay.
10,044.
Oh, 10,044. I'm sorry. Not very good with numbers.
Yeah, so something's not going right. I'm getting like negative 96,000.
Okay. Hold on just a minute. We'll look at it. All right. Now, what if I wanted this rounded to the nearest kilometer?
It must be 10,044.
And you make sure you put kilometers on there because we will be looking for units for your answers. And remember that the answer should actually be a complete sentence. So the distance between Seattle and Salzburg is 10,045 kilometers. Okay? All right. Now, what if I was going to tell you that you were going to fly there, and we want to know the distance of the flight, but you're going to fly eastward? So that means starting in Salzburg. So if we start in Salzburg and fly east, that means we're flying the far distance around. Why do you think I keep mentioning this? Okay? So you be ready for it. All right? So instead of 135, you're going to use 360 degrees minus 135 degrees to find your angular distance, because you want the rest of it, the other side. Okay? And if you knew the circumference of the Earth at that point, you could just subtract, but you don't. So don't think you can just do that. You could at the equator, but nowhere else. Okay? All right. So what we're going to do is we're going to practice a few of these. Now, what if these two cities had been on the equator? Which part of this formula would I not need if they'd been on the equator? I wouldn't need the cosine part. And why is the equator different? Because it is a what? A great circle. Okay? All right.
So I figured it out. I didn't have my calculator in that mode.
Ah, okay.
So then,
All right. So that's the end of the recording. So what we're going to do is we're going to look at a few problems together.